review a little bit of the fundamental theorem of calculus that we've talked about, see it put into action a little bit. So, first, a little reminder what part 1 is, that the derivative is the function with the x value plugged in, and a slight reminder of what part 2 is, anti-derived, plug in b, plug in a. So, use FTC1 to find the derivative of a function. We're finding the derivative. Make sure your constant's at the bottom. Plug that in. We would get sine to the 4th of 1 over x. But then we have to multiply by 1 over x's derivative, which is negative 1 over x squared. We end up with negative 1 over x squared times the sine to the 4th of 1 over x as our first derivative. Similar idea here. Constant's at the bottom, so we plug in our radical x, we get cosine of radical x over radical x, while x to the 1/2 derivative is 1/2 x to the negative 1/2, or 1 over 2 radical x, so we have to multiply by 1 over 2 radical x, and we end up with cosine of radical x over 2x. This last one, if you notice right off the bat, our constant's at the top. That's no good. So we're going to change it. Go from 1 to 1 minus 3x of u cubed over 1 plus u squared du. Keep our negative. Plug in our 1 minus 3x. By the derivative of the 1 minus 3x. So we get 3 times 1 minus 3x cubed all over 1 plus 1 minus 3x squared. As the derivative, I won't make you cube that function. Now, FTC part 2, it says use the graph to give a rough estimate of the area under the curve y equals x to the negative 4th from 1 to 6. So we're talking this area, and there is a little bit of area there because it's not actually touching the x-axis, just appears to in our picture. So, looks like it might be, take an educated guess, I'd say somewhere around a half. Because remember, this is 1, so 1 by 1 would be 1. This is smaller than that, so I'm going to estimate a half. Now, let's find out, because we need the integral from 1 to 6 of x to the negative 4th dx. Anti-derive, we get negative 1/3 x to the negative 3rd from 1 to 6. So negative 1/3 times 6 to the negative 3rd minus negative 1/3 times 1 to the negative 3rd. To the negative 3rd is 1 over 6 cubed, or 1 over 216, so we get negative 1 over 648 plus 1/3. Well, 1/3 is going to be 216 over 648. We end up with 215 over 648, or approximately 0.3318. Let g of x equal the integral from 0 to x of f of t dt. So g of x is the area underneath. It says where f is the function whose graph is shown. Domain being 0 to 4. At what values of x do local maximums occur? Well, if g of x is our integral from 0 to x of f of t dt, to find a maximum, we need to look at the derivative. Well, the derivative of x, based on FTC part 1, will be f of x. So we need to know when f of x changes for a max from positive to negative, and for a min from negative to positive. So there's a maximum at x equals 3 and a minimum at x equals 1. Now, where does G attain the absolute maximum value? We have to consider a few places, or think common sense-wise. We've got some negative area, then we have some positive area, and it cancels out this area about here, and continues to add up till it gets to 3, and then negative area starts canceling it out. So it would be at its highest area at x equals 3 with a value of g of 3. Now, what intervals is it concave down? Well, let's talk about concavity for a second. Concavity comes from the second derivative. Well, if g prime is f of x, g double prime of x is f prime of x, or the slope of the picture we have. Because it's a picture of f prime would be the slope. So concave down would be where the slope is negative. So that's going to be from 0 to 1/2 and from 2 to 4. And they want us to sketch a graph of this. All right. Based on what we know that this graph is concave down from 0 to 1/2. We also know that it is a negative value, and it reaches its maximum at 4. So, and its minimum at 1. So it's going to look something like this. It's just a rough sketch based on what we know. Max, min, and it actually needs to be concave down for a little bit here. And it is concave down from 2 to 4. So, sketch that a little bit better. There we go. Your graph might not be identical to someone around you, but as long as it meets those properties, it can be correct, so they don't have to all look alike.